physics, a quantum is the smallest discrete quantity of a physical entity. For example, a photon is the quantum of light, while an electron is the quantum of the atom. As we all know, in physics, the quantum of light is the photon, while the electron is considered the quantum of the atom. For example, a photon is the quantum of light, while an electron is the quantum of the atom. As you know, quantum phenomena are among the strangest phenomena that science has ever discovered. The phenomenon where two particles of matter are tightly bound together, no matter how far apart they are, even over distances spanning light years. The state of one particle will instantly affect the state of the other through their strong connection. In other words, when two electrons are close to each other, their quantum states can interact. If we now separate them far apart, even by hundreds or thousands of light years, they will still maintain this connection. When you gently shake one electron, the electron on the opposite side instantly reacts to this movement, even faster than the speed of light. Faced with this bizarre phenomenon, the British genius Stang reached his final conclusion. The event was so anomalous that it was nearly impossible to occur. Spooky action at a distance. The recently completed experiments have provided the clearest evidence yet proving that the phenomenon of quantum decoherence truly exists. And once again, it reaffirms what we have always known. This universe remains as wondrous as ever. The quantum phenomenon itself largely exists only in theory and is very difficult to verify in practice. Although physicists can easily observe this phenomenon, we cannot determine whether some invisible factor is influencing the state of the two particles. The results obtained appear to be similar to what we expected. Why can these two particles connect in such a strange way, remaining identical even when far apart? Simply by precisely determining the parameters of one particle, whether separated by a few meters or light years apart, scientists can deduce the state of the remaining particle. Over the past century, numerous experiments have been conducted to demonstrate quantum entanglement, but to this day, no complete explanation for this phenomenon has been found. Even an eccentric genius like Stang, when faced with the final decision, could only see it as a strange, distant influence, never finding a thorough explanation. Mr. Stang does not deny that this is a quantum deception phenomenon, but he suggests that there may be some hidden variable values that led to this occurrence. In the 1960s, physicist John Bell designed a special experiment to test whether entanglement truly exists or if the experimental results were influenced by some hidden variable. John Bell's experiment involves two separate measurements on two entangled particles, comparing the results to determine which option is more convincing. According to Elizabeth Sidney from the journal Nature, John Bell statistically demonstrated that the correlation between results exceeding random thresholds cannot be explained by the hypothesis of hidden particle properties. Instead, the results show that measuring one particle inexplicably altered the properties of the other. Scientists soon realized that physicist Bell's experiments had certain limitations, leaving room for alternative interpretations. One of the knowledge gaps may lie in the fact that particles share information at the speed of light, while our current measurement tools are still too rudimentary to keep up with this phenomenon. The final result may have been skewed due to some particles not being measured accurately. In 2015, these two loopholes were finally resolved through a historic experiment. This experiment pushed quantum entanglement past its toughest test by eliminating both of the aforementioned possibilities. However, there remains another gap, the gap named the freedom to choose attributes. Elizabeth Sheep argues that every time we repeat the Bell experiment, we implicitly assume that, when conducting experiments, scientists can choose the measurement method applied to each photon in a pair of light particles. However, some mysterious effects may simultaneously influence both particles and the testing method being used, or they may affect the measurement choices. More reasonably, they narrow down the feasible options to create a clear image of the knot. According to Andre Friedman, a member of the research team at MIT. To put it simply, imagine the universe as a restaurant with a menu of 10 dishes to order. You thought you could order any dish from that list of 10. But then they informed you that the chicken was sold out, so in the end, you could only order 5 dishes. Still free to choose the remaining 5 items, but from the very first moment, even with quantum experiments, there may still exist undiscovered constraints. The constraints in your choices along with those mysterious factors may lead us to believe that quantum entanglement is real. One of the factors that frequently causes errors is gravity, whose influence likely limits the measurement methods we can perform. Because we conduct these experiments on Earth, where gravity has existed and governed since the planet's earliest days. So how can we overcome the limitation of free choice when the universe itself restricts our ability to measure? Previously, scientists attempted to address this gap by implementing a random number generation system. At the last minute, they randomly selected a few properties to measure before the particle reached its endpoint. This means the particles almost don't have enough time to exchange information with each other, and the final result will only make it seem like they're cheating. As Mr. Sten had predicted, this experiment is entirely feasible, but it only eliminates the influence of hidden variables for a few microseconds before the material particle is launched. But what if this variable had already affected the particle before that moment? A research team consisting of scientists from MIT, Vietnam National University, Austria, and several other research institutes in China and Germany has discovered a way to use light to extend time. Help completely eliminate invisible influencing factors from the testing process. This experiment aims to determine the positions of red and blue in certain specific properties, then proceed to measure the particles. The two telescopes will be arranged to observe whether the reflected light is blue or red. The detected color will determine the property to be measured in the counterpart particles, as the color of light cannot change during propagation. Therefore, any influencing factor does not affect the particle, and the particle's properties cannot be determined before measurement is performed. The light being used comes from a star very far away, and if those particle properties had been predetermined, they must have been set 600 years ago. This experiment cannot close all gaps in the issue of free will, but for the first time, we can confirm the existence of a strange remote interaction effect, at least one that has persisted for the past 600 years. The scientists' next goal is to push beyond the current 600-year limit. They may achieve this by utilizing light from more distant stars, even reaching billions of years further into the past. But then, where is the stopping point? Is the Big Bang the starting point of the universe? Perhaps the universe itself has limited the choices of particles from the very beginning, as every measurement has been predetermined since the moment of the Big Bang. Bell's experiment cannot be extended to the time before light appeared, so the freedom of choice loophole will never be fully closed. Nevertheless, Friedman still asserts that those infinite possibilities are so captivating that they cannot stop exploring. This is a favorable opportunity for us. We will gradually fill this gap while further strengthening confidence in the proposed quantum hypotheses. Or we will uncover evidence of an entirely new physical phenomenon. Today, quantum physics is widely applied in many fields, such as quantum computer manufacturing or quantum teleportation technology. We still don't fully understand quantum mechanics or quantum theory, yet we can still apply them to achieve technological breakthroughs. Scientists have successfully transmitted information between two chips without using electrical wires, instead leveraging the phenomenon of quantum entanglement. To achieve this breakthrough, the research team generated multiple pairs of quantum entangled photons while encoding quantum information into them. Ensure that the information is accurate and does not affect the quantum state of the particle. Although this success has only been achieved in the lab, the immense potential of this new breakthrough cannot be denied. Breakthroughs in quantum computing are becoming increasingly common, particularly in the discovery of new methods to harness quantum entanglement. But in essence, it remains highly difficult to manipulate, nearly impossible to control the quantum flow at will. Operating systems that transmit signals via quantum links remain highly cumbersome, not to mention prohibitively expensive. But breakthroughs like this research give us hope for a bright quantum future. When everyone can hold quantum computing power in their hands and browse the web on an absolutely secure internet. Transmit signals securely, free from external interference. The deeper we understand the quantum world, our microscopic realm, the more unanswered questions we can resolve. From there, we can gain a deeper understanding of the nature of our own existence and the universe.